Unit 1 is intended to be a review of the essential topics from high school chemistry. Therefore, it is very important to be able to master the topics that we review here in order to succeed in the course, as we will build upon these concepts as we study the more advanced topics later in the course. Chemistry is often referred to as the central science, and this is because whatever discipline you're studying, whether it's medicine or dentistry or pharmacy or biology, environmental science, geology, physics, or math, chances are that the study of chemistry will help you to give you a much better understanding of your discipline. The ability to make measurements is fundamental to any discipline in science. The International System of Units, or SI system, is based on the metric system. The SI unit for length is the meter. The SI unit for mass is the kilogram. The SI unit for time is seconds. The SI unit for temperature is Kelvin. Now this differs from the more commonly used metric but non-SI unit, degrees Celsius. The SI unit for the amount of substance is the mole. The SI unit for current is the ampere, and the SI unit for luminous intensity is the candela. The SI base units are used to define all of the other SI units that we commonly use. So the SI unit for energy is a joule and has the capital symbol J, but it can be defined in terms of its base units, which are the kilogram times meter squared per second squared. The SI unit for pressure is the Pascal, or PA, which has base units of kilogram per meter per second. The SI unit for force is the Newton, which has a capital symbol N, which is expressed in base units, kilogram times meters per second squared. The SI unit for electric charge is the Coulomb, given by the capital symbol C, and that can be expressed as its base units of an ampere times second. SI unit for voltage or electrical potential is the volts, given by the symbol capital V, and it has the base units kilogram per meter per second per coulomb. And finally, the SI unit for frequency is the hertz, given by capital HZ, and has units of seconds to the negative 1. Measurements can come in a wide range of sizes, anywhere from the size of individual crystals, which are on the order of 10 to the minus 2 meters, to the size of bacterial cells, which are about 10 to the minus 6 meters, viruses, about 10 to the minus 8 meters, to the length of a chemical bond, which is about 10 to the minus 10 meters, or 1 angstrom, to the size of individual atoms, about 10 to the minus 11 meters for a hydrogen atom. A major advantage of the metric system is that it is based on powers of 10. So for example, a kilogram is 1,000 grams. A gigahertz is a billion hertz. Similarly, a centimeter is 1/100th or 0.01 meters. And a micrometer is a millionth or 10 to the minus 6 meters. This table represents the most common prefixes that are used in the SI system. You are responsible for knowing the prefixes highlighted in blue. An important skill in chemistry is being able to convert between various units. And in the metric system, the prefixes, for example, kilo here, have well-defined meanings. So you might know that kilo means 10 to the power 3, so that there are 10 to the 3 grams in a kilogram. Similarly, nano in nanoseconds means 10 to the minus 9, so we would know that there are 10 to the minus 9 seconds in a nanosecond. This unit here is a very special unit of length that's often used in chemistry, known as an angstrom. And an angstrom is equal to 10 to the minus 10 meters. The angstrom is particularly important in chemistry because it is the approximate length of a chemical bond. Now, if we want to move in the other direction to convert from moles to micromoles, we might want to use a technique known as dimensional analysis. So starting with a mole, we know that there are 10 to the minus 6 micromoles in a mole. And so in this case, we would divide by 10 to the minus 6. Here we would notice that the units, in this case the moles, cancel, leaving us with units of micromoles, which is the unit that we want. So dividing this out, we would see that there are 10 to the plus 6 micromoles in a mole. Similarly, if we want to go from meters to picometers, using the same technique of dimensional analysis, starting with 1 meter, we know that 1 picometer equals 10 to the minus 12 meters. So we would divide by 10 to the minus 12. Keeping track of our units, we see again that the meters cancel, leaving us with units of picometers, which is what we want. So dividing by 10 to the minus 12 gives us 10 to the plus 12 picometers in 1 meter.
In this question, we were asked to convert from cubic millimeters to cubic decimeters. So the strategy here is to use our knowledge of SI prefixes to do the conversions. Then we will do the actual calculation using a technique called dimensional analysis. Now I don't happen to know the conversion directly from cubic millimeters to cubic decimeters. However, from my knowledge of SI prefixes, I know that 1 millimeter equals 10 to the minus 3 meters. And that's simply because the SI prefix milli means 10 to the minus 3. Similarly, I know that 1 decimeter equals 10 to the minus 1 meters. And again, that's simply because the SI prefix deci means 10 to the minus 1. Now that we have our conversion factors, we can start to work on the calculation. So starting with the value of 1.2 times 10 to the power 2 cubic millimeters, which was the value originally given in the question, we can convert our cubic millimeters to meters using our conversion factor of 1 millimeter equals 10 to the minus 3 meters. Now you'll notice here that our units were given in cubic millimeters, but our conversion factor is only in millimeters to meters. So to convert from cubic millimeters to cubic meters, we would have to raise our conversion factor to the power 3. Next, if we want to go from cubic meters to cubic decimeters, we would use our conversion factor, which is 10 to the minus 1 meters equals 1 decimeter. Again, this conversion factor only goes from meters to decimeters, and if we want to go from cubic meters to cubic decimeters, we would have to raise our conversion factor to the power 3. Now, normally we would simply just plug this into our calculator, but I just want to expand the brackets to show you the math that's going on. So here we have 1.2 times 10 to the power 2 cubic millimeters, which is the value that was originally given in the question. Now, if we want to expand out the brackets, you'll notice that we have an exponent raised to the power 3. Now, you might remember from high school math that when you have an exponent raised to the power 3, you simply multiply the exponents together. So here we have minus 3 raised to the power 3, which is equivalent to minus 3 times 3, which gives us 10 to the power of minus 9 cubic meters divided by cubic millimeters. And you'll see here that our cubic millimeters cancel, leaving us with units of cubic meters. Moving to the next conversion factor, we see that we have an exponent of 10 to the minus 1 raised to the power 3. So that is like minus 1 times 3, which is minus 3. So here we have cubic decimeters in the numerator divided by 10 to the power minus 3 cubic meters in the denominator. And again, we'll see that the cubic meters cancel, leaving us with units of cubic meters. Now we can plug this into our calculator, and we would get an answer of 1.2 times 10 to the power of minus 4 cubic decimeters, which is our final answer.